Alright, hello everybody. Welcome. I'm just going to do a quick update video for everybody, slash summarization of everything. So over this last weekend, I spent about 30 hours. I found out that the Air Force doesn't use a newer version of Unreal Engine 5, like 5.1.1 like I was using. They use an earlier version, like the first Unreal Engine 5 version. So I had to remake everything. And fortunately, during that remake process, I ended up increasing performance by about double, getting a better FPS. And a few things look a little bit smoother as well. Was able to refine a few things. But in any case, I'll show all of the different examples that I have. So starting with the first area that we teach. These are the examples I have for upwelling. So cold water comes up, warm air goes away because we have winds that are parallel to the coast and go to the right because of the rotation of the Earth. And then the opposite is they're coming parallel to the coast from the opposite direction and go towards the coast, creating downwelling. If I turn around here, then we have another example. I went ahead and made my own interactable actor rather than from the... So now I'm using completely my own stuff that's made from, built off of the original template that Epic Games has for everyone. So I made an interactable object. So you just rotate this around and it'll show you whatever the tide is that you end up having. You just keep on rotating around. You can see that they have we can see that we have the poles here, so this is rotating around the Earth, so that they can visualize so spring tide and neap tide and how that relationship goes. And we have the sun, obviously, since it's yellow. I have this outside area here to make it a little more friendly and inviting. Before I had just a hallway, and the students said that it was the start of a horror game, so I opened it up and put birds and stuff in. When you get further inside, the birds quiet down, and I can adjust that as I please, or change the bird to something else, like piano music. But we've got hot to cold and cold to hot using Niagara particles. Jiggle around, and we talk about how a warm particle has more space in it to hold more water vapor, and so that's the basis of warm versus cold air and stuff like that. And then here we have the adiabatic process and the pseudo-adiabatic process, a reversible process, and then an irreversible process over to the right. So yeah, anytime you've ever experienced a rainstorm and then afterwards it feels like a lot nicer and a lot warm, a lot drier and not as muggy, well, that's because we have less moisture in the atmosphere when that thunderstorm's all over with, versus with this, if you have no actual thunderstorm, so the atmosphere hasn't lost any water vapor, then there you go. Yep. So they get like a more visual representation of what's going on. And then right here, talk about vorticity and how we have shear vorticity. In the classroom, we have an example. We have two students off to the sides, and then we'll have either ourselves or another student all volunteer. All are volunteers, and we push each of them off. The other ones spin off to the right and left, and that's teaching them the shear vorticity. And then the curvature vorticity, they're not really getting that, and so that's when bringing them in here, they go like, oh, because they're seeing all of these particles coming in and going around, so that's all the downward vertical motion. We have more mass that's coming down here and building up and getting our higher heights over to the right and lower heights or lower pressure to the left. And then we also have all of this chimney effect, upward vertical motion coming up here and turning to the left here. So that's nice. And then here, I use this room. I need to put like a button in here. I need to add a button to take away the highs and lows and the extra stuff that we talk about in a later part of the curriculum, so that I can use this room over and over again. But here, talk about the 3-cell model, as you can see up the top, the chimney effect, the damper effect, and how the chimney effect has a low at the surface, damper effect a high at the surface. They can always associate those with that, and they can see a visual representation of the large scale effect, and then each of those large scale effects intertwining together and creating essentially gears, and they get the gears spinning in their head, which is nice. And right here I can switch from summer to winter. Right now summer, so that North American low is really strong because lots of heat, and we've got the Pacific high that's over off the coast of Baja California, and then the Bermuda Azores high that's over there in the Atlantic. And as we move this, those will shift, and then we'll have the Aleutian low come on over here, and then the Canadian high gets stronger because it's winter, it likes the cold, and then the North American low gets weaker because it doesn't like the cold, it wants to be warm. And then we teach also about tropical storms and how they roll off of Africa, come across the Atlantic, and then because of the Bermuda Azores high, they spin up and come up and into the Gulf and go up and along the East Coast as well. So that's why we end up getting so many hurricanes and tropical depressions in our area. And then right here I have another interactable actor. We can spin around, so we can just stay in one spot and visualize everything, or we can go up and get a little bit closer to check things out. But each of the other lows that we talk about, and we can go ahead and slide those back and forth, and they get a full-scale example of everything. We can get up a little bit closer. I can also I could change it so that you could actually go inside of it. Right now you can go on top, look at, and they can kneel and look down at it. Right here, what the big takeaway here that's really nice is that the fact that when this is spinning around, it's turning to the left, up aloft, but once it gets that frictional force effect, it then comes down and then turns to the right. And they love that because being able to see what exactly is happening is great for them. They're loving it. I'll go back the other way real quick. So I'm going to be teleporting real quick. I have level streaming, so each of the levels deactivate and the lights turn off, because right now I have each of the lights movable so that we actually get proper lighting, and I don't have to bake the lighting. Performance is pretty good, so I don't think I have to change it to static or dynamic. So right here we have land breeze and sea breeze, as you can see, land breeze, sea breeze. So during the night, we end up having the water get warmer. So warm air rises over the water, and then cold air sinks over the land, and that's how we end up getting a land breeze. And over to the right, we end up getting a sea breeze, because during the day, the land is warmer, so it has air that rises. I could possibly add some clouds in there, so clouds form up on the over the land versus over the sea in this situation. I could add a little bit more now that I'm thinking about it, but always adding, right? In this part, the 3-cell model that we were showing over there, we're showing the 3-cell model and elaborating on it and showing that we have lower heights and then going to higher and higher heights as we get to the equator, and seeing this visual scale going up and progressing, and the interchange. So this is one singular spline, and using Niagara particles that just go, the arrows just follow along that spline. And so if I end up leaving the area and then I come back, you'll see that we can start talking about it, and as it's coming down and building out the entire simulation, then we can talk about the polar high and how it moves on to the subpolar low and comes up and has upward vertical motion while we have cold air sinking, and then comes over to the subtropical high, and we have the downward vertical motion, but we have the upward vertical motion of warm air rising, which creates the higher heights, but it's not so high as the equatorial low because we have that downward vertical motion. And then for the equatorial low, it ends up being the highest because we have both warm air rising and that upward vertical motion from convergence at the surface. So, yep. And so you see that's coming back around. I have these pillars over here on the right and left so that they don't see the interchange. So yeah, the loop, it's all a single loop. And then here we've got a stable wave. I will get all of these animated, and yeah, in a different video I have an animated weather system that's moving through and has proper stacking. For now, all of these are just static models so that they can see, like, okay, so with a stable wave, we're not talking about really anything aloft. We're just talking about, that stationary boundary with a low, and then we need Pedersen's rule to kick things off. Then Pedersen's rule happens, we get an unstable wave, and then we got the late mature, I need to have an early mature wave, then a late mature wave, and then a decaying wave, and an entire process to that I'll talk about at a different time. And then we have the warm occluded wave and cold occluded wave. I need to separate these a little bit. Yeah, I'm just noticing that. I'll separate them later. So talking about the trough of warm air aloft in this situation works out really nicely, and we can talk about it how right here in the center with the cold air, we've got the basically the land mass here in the center, and then each of the oceans, if we're talking about America, for example, or like any continent, honestly. So yeah, there's that. And then right here, I was teaching our this little bit of information, and we have like this concept, the amount of information that we're teaching in this area. They think that it's this grandiose thing, and they think at way too many levels in the atmosphere, when we're just wanting to think, okay, we have a trough, we have a low below it. Okay, what's going to happen? All right, well, if I grab this and I start this little simulation, if we have upward vertical motion and we have that mass being taken up and out, we're going to get lower and lower pressure. Whereas if we move it downstream, it's going to get more and more pressure, and so it's going to go cyclolysis, and it's going to get weaker. That L gets smaller and weaker until we can go ahead and move it on back over to this, and we can have cyclogenesis happen again. And then the same thing for this. Highs don't like, highs want to have more mass, so anti-cyclolysis, anti-cyclogenesis, and then we can go all the way through the process. I'll start on the other side. I still need to make these two, Mountain Breeze and Valley Breeze. I do have that in another video, but right here, same example, but we're talking about the mesoscale, so smaller scale now in this section. So we're talking about lake breeze and land breeze rather than sea breeze and land breeze. And then we talk about the non-supercell tornadogenesis, supercell tornadogenesis, and supercell hail, and how all of that is generated and created, and the different steps to it, and what we need to have in order to have a supercell versus a non-supercell. And we have two different interactable actors here, and that we have the El Nino, which right now we're crossing into an El Nino phase ourselves. And if you change this over to an El Nino, well, we get warmer waters off the coast of North America, and we get more storms in the central. Well, there's also other effects that we teach that are for North America, and I'm going to work on another model or like another presentation of the information to show how the long wave changes and feeds in more moisture, in this situation, more moisture into the southern North America, and how that has a big scale effect on things, and why the El Nino Southern Oscillation is such a big thing. And then we've got our stable. So stable is going to be on the east side, and then with the neutral, it'll be on both sides. I might have to adjust this a little bit. It's going to go on both sides, and it's on both sides. There you go, neutral. I just need to adjust the words or something. And then this unstable is going to be on the west side of the trough axis. So we call this the Wuffness monster. There's a whole acronym to it. But yeah, that's that. Yep. All right. Have a good day.